Okay. So, like I had mentioned before, I graded everyone's homework number 2, and then accidentally left it on my desk at home when I came in today. So I'll have it in my office tomorrow and Friday if you feel a burning desire to have it back. If not, I'll give it out on Monday. That was, number 2 was by far going to be the longest homework assignment of the term, right? So you see the one that this week should have been significantly less than that one, and next week is only a couple problems. So if you're worried about the workload for this, right, there's kind of a little bit of a front-heavy stuff, and then the homework will be significantly less. There were a couple things that I noticed. And I forgot my notes on them with the homework. So the first was the divergence of stress, right? So, right, a lot of people got the definition messed up, right? So this is partial sigma ij partial xj. Now, we have a repeated index here of j, right? So we have to sum over j, right? So that means if we sum over j, we only have one free index I. So how many terms does the divergence? 3, not 9, right? So a lot of people wrote the answer to that question as 1 partial sigma 1 1 partial x1, right? Sigma, right? They wrote out all the terms correctly, right? And left it just like this as a 3 by 3 matrix, right? That's just the matrix of the partial derivatives. That's not the divergence of the stress field, right? The divergence is summing over, right? So I think it's a good thing to maybe take a step back and remind us of some Calc 3 things, right? So the gradient of a scalar field, right, where x is a scalar, right? So we have the gradient of a rank 0 tensor is what type of object? It's a vector, right? So it's going to be a rank 1 tensor, right? And so in indicial notation, right, that's going to be partial. Just let me change this here just to avoid confusion, right? Partial f, partial x1, partial f, partial x2, partial f, partial x3, right? That's the gradient. So what's the gradient of a vector field? It's going to be a second rank tensor, right? So if right, this is partial fi partial xj, right? And then let's be really careful about this. Actually, we play a little fast and loose sometimes. So if the gradient of vector f That's the gradient of Fi. Right, this is partial Fi partial xj e hat I. Right, when we write things in indicial notation, we often leave off our basis vectors, right? But so this is the gradient of a vector is a second order tensor. Right. We have the first set of bases that are the original basis of our vector. The second ej are the basis of our spatial coordinates that we're taking our directional derivatives with respect to. Okay, so what about the divergence of a vector field? Right, the divergence of a vector is going to be a scalar. Right? The divergence of a tensor is a second rank tensor is a vector. Right? And then what about the Laplacian? Right? This is for a scalar field, right? It's the divergence of the gradient, right? So the gradient, if it's a scalar, this is going to be now a vector. Then we take the divergence of that vector and it gives us a scalar, right? Does anyone remember what the physical interpretation of the Laplacian is? Right? Right, the gradient is the direction of steepest descent at a point, right? The divergence tells you, right, how the spread of the vector of the flow at a given point, right? If I have a vector going in, right, it tells me what. What about the Laplacian? Right? The interpretation of this one's a little interesting. It's the deviation of the value of a function at a point from the neighborhood around it. Right? So if something is spiky, right, the Laplacian is large. Right? This is why right, think about it from a diffusion equation, right, or a heat transfer equation. Right? If I've got a single point that has a high chemical concentration, but the rest of its neighbors are small, right? I'm going to lose. That concentration is going to diffuse out very, very quickly. All right, and so that's the interpretation of the Laplacian. So the Laplacian of a tensor field, right, or let's think the Laplacian of a vector field, right? So we're going to take the derivative, or we're going to take the gradient, which gives us a second rank tensor, and then the divergence, which takes us back to a vector. Right, and the same thing. So it scales. It scales up. Gradients take you up a rank. Divergence takes you down. Okay, and then curl keeps you the same, but we won't talk about the curl too much. If this was a proper continuum mechanics course, we would mention it. The only time we'll mention curl will be briefly in the next lecture on dislocations, right? When we talk about where you have an incompatibility of your deformation field at like a dislocation core, right? That's a spot where the curl of the deformation goes to 0, right? So if you have a continuous field that's compatible, right, that follows all your rules of continuum mechanics, the curl of those tensors have to be 0 everywhere, right? Meaning I'm not opening holes in my material, or points that are next to each other don't overlap or cross through each other. So that was, I think, the biggest issue. There were some other issues of people not reading the question and doing work but not providing the answer that was there. Especially the one where you had to go through and it gave you the deformation field. You had to work through and find all the tensors and then asked you to apply the small strain approximation. A lot of people just jump to the small strain approximation right from the get-go. And so that was a couple off there. The interesting thing was I didn't notice a really strong correlation between the grades on the first homework and the grades on the second. There were a couple people who did well on one and not on the other, and, right? So, but the average was about the same. So, okay. So, any questions about? I know there's a ways off still. The homework that's due next week. I don't think anyone's probably started it because you were doing the one that's due today. Okay. And hopefully it wasn't. There was nothing too bad on it. So I want to. So on Monday we'll take. I'll go through. I'll take any questions, but I want to do a little bit of some viscoelasticity problems. I think the rubber elasticity stuff, yeah, there's some mathematical details in there, but conceptually it's pretty easy, right? You've got this random walk kind of idea, and I got a formula that I can plug in to get the chain-to-chain distances. The main ideas are pretty straightforward. Viscoelasticity seems to be a little bit more of a tricky concept for some people. So I want to work through a problem, right? So I've got some kind of polymer rod, right? It doesn't really matter what it is, but we're 200 millimeters long and 20 millimeters in diameter, right? And this rod is put into a load frame, and we give it a 600 Newton tensile load axially, right? And we keep it at a constant load for a long time. And we record the length. All right, this is the change in length. All right. For a long time. And we find it fits an equation of this form. Right. That's just, we plotted the data points and then did a exponential curve fit to the data points, right? So delta, so the units here, delta is in millimeters and T is in hours. Okay. So we did this experiment. And so there's a strong time-dependent response. I'm assuming that it's viscoelastic. Right, this is not a plastic flow curve. How would I verify that it is linearly viscoelastic? The strain versus the... Well, yeah, okay, so that'll give me a straight line, right? But, right, that's, we could see that just from the displacement relation, right? That doesn't... Right, what does it mean that something is linearly viscoelastic? What does any linear function, what does it mean for any function to be linear? Right. If I have a linear system, what does it mean? It's a black box. Right? This is something you learned in differential equations. Or you should have learned in differential equations. Right? What does it mean to be linear? It's
the derivatives are cut. T2 dx dx
it's,
the stress has a direct mapping to strain.
okay, so it's invertible, right? That's a big one. But there's something about, right? So if I have some function f of x, right? If this is linear, it means that f of ax is equal to af of x. Right? Right? If I scale my input, my output scales by the same factor. Right? Right, that's the big thing about a linear system. So how would I verify that this polymer is actually behaving linearly?
Change the stress.
Yeah, I would change the stress, right? So for linear viscoelasticity, right, we're going to have our strain as a function of time is equal to, we're keeping a constant stress here. What letter did I use for the creep modulus in the notes? The creep modulus. Is it J did I use? Or G? J. Okay. Different books use different things. And the one where I'm looking for this problem uses D. I didn't want to cause confusion. Right? So we have a modulus, a time-dependent modulus that relates stress stress and strain, right? So if our strain is given by this is an engineering strain, and our stress is equal to force divided by area, right? So we have epsilon tau by sigma is J of t, right? This is only a function of time, right? Our modulus is not a function of applied force, right? So that means we can vary our load, right? But J of t should be constant, right? So that means if delta I right? So at our initial time, right, if our initial stretch is the same, right, we're going to be, or if our initial loading increment, right, so we have a curve, I mean, it's exponential curve, right, so it's going to start at 0.20 and go something like this. Right. This is delta, this is time. So time equals 0. My initial stretch is 0.2. Right? If I were to double the load, my starting point would be 0.4. Right? So I have right, if I were to double the force, each term of this in here would double. So my initial stretch would be 0.4, and then my rate would be 0.3. Right? So this is at 600 newtons. If I made that 1200 newtons, I should get an equation that looks like this, for this to be linear viscoelastic. Okay, so let's assume that it is. So what I want to do is find J of t, right? And then I want to find the unrelaxed modulus and the relaxation time. Okay. So how do I find my modulus? Right. So strain right? Strain is easy. EXP. Right, and my original length was 200 millimeters. Right, so that's my strain. My stress is 600 newtons divided by the area. Right. And my area is right. So this is approximately 1.9099. right, pascals. So our modulus is simply right. So that's my modulus, right, and it's going to look something like, right, this is t in hours, this is jt, right, it's going to have the units of Pascal inverse, right, and it looks something like this. Okay.
Why did you take the engineering strength?
It's slow, right? Right. We could do we could work it out with the true strain, but I just kept it as the engineering strain. Okay, so do I ask for the relaxed modulus or the unrelaxed? The unrelaxed and the relaxation. Time. So what do I mean by the relaxed modulus? Right.
The modulus at 0.
Well, that's the unrelaxed, right? So that's the instantaneous. That's when we first put our load on.
Okay, that's called unrelaxed.
That's unrelaxed, right? Our system hasn't settled into,
Okay.
right? So the relaxed modulus is at
approaches.
long time, right? So the relaxed modulus is at time goes to infinity, right? And so if time goes to infinity, our exponential term goes to 0, right? So that's just 0.2 over 3.8 times 10 to the 8th, approximately 5 point. Right? And the
10 to the 8th, right?
yeah. I wrote 10 to the infinity, huh?
I was up to 6.
Yeah. 8. Right? And then the unrelaxed modulus is instantaneous, where time goes to 0. Right? So,
0.05.
right? So that gives us 0.05 over 3.8 times 10 to the 8. Right? So that gives you basically the difference between the relaxed and the unrelaxed gives you the difference in stretch rate between when you first put the load on and after you keep it there for a long, long time. Yeah.
The relaxed part, has it anything to do with the inelasticity?
There's you mean in a physical sense, right? So yeah, there's we're not thinking about the energetics here, right? It's just this is the kinematics of it, right? This is the how it goes. What is the energy going to look like? Right? We're going to have a different path coming back, right? So there is dissipation there. I got to think about how those two actually relate. That's an interesting question, and I don't know the answer right off the top of my head. I'll look. Right. Well, so okay. So if you remove the stress, right, it's going to come back slowly on time, but the strain, the power is 0 there, right? So the dissipation is the whole area under the loading curve. Huh. Okay. Yeah, I got to think about how that would. Okay. So we're going to use the elasticity, the fact that it's linear viscoelastic, right? And if I were to hypothetically subject this to a load of 400 newtons for 5 hours, what would the displacement be? Right. So how do I go about this?
It's linear, so at 600 you know the delta t. So
Yeah. Right. So I could just do delta of 5 hours, right? My current load divided by my original load times my original. Right? Right, I just scale my displacement relationship. Right? Okay. So the next bit we want is, again, we're going to keep our 400 Newton load, right? And we're going to hold it for a long enough time that right, the rod basically right, so the rod stops elongating, right? So if we go by the equation, it's never going to stop, actually, right? So we need to, when we say the rod stops elongating, that's a practical measure, right? So how long, right? How long does this take, right? And I also want to know the final elongation, right? And what's the immediate? elongation, right? And how long does it take to get that? What does immediate mean here, right? So, what's a practical kind of consideration for this, for how long this takes, right? It's going to take an infinite amount of time before it actually stops stretching, right? But right,
Question of convention. Right?
it's a convention of convention, right? So we have to define some kind of convention as when we're going to say, right, when it's reached 90% of its final elongated length, right? Or when it's reached 95% or 99%, right? We have to pick some value, right? And we'll say, you know, one thing, there's two ways. You can either say, I'm going to see how long extrapolate out and see what the final length would be, and then take some fraction of that. Or I can look at the rate. And I know that the rate is going to go to 0 asymptotically. And I can say when it reaches 95% or 0.05% of its, when it's only deforming at 5% of its initial rate or something like that, right? So there's two ways you can do it. We're going to just pick the first one because it's really convenient. So we'll define the long time as is the time to reach. Oops. The time to reach 95% elongation, right? So if we look at the delta for infinite time, we end up with 0.2 times 2/3, right? This is 400 over 600, this 2/3. Instead of 2/3, let me just write 400 over 600. And so that gives me 0.1333 millimeters. Right. So that's my final elongation. So we want long enough to mean where our elongation is a function of time divided by our infinite elongation is 0.95. All right, so we can write this as 0.20 minus 0.15 ESP 0.1 T. Right, and notice that this time then becomes independent of our actual load. Right, so this time is also a constant. Right, and so if we solve this, equals 0.95. Right, if we solve this, we have T is like 27 hours. Right, so basically after a day, it's stretched almost as much as it's going to stretch from now until the end of time.
So the T is in seconds or in hours?
T is in hours.
inside also. Exponential 0.1t.
Yeah. So we defined, when we measured our curve, we defined t as to be hours and delta is in millimeters. Right? Right. And then basically the short time is the exact same procedure. All right, and we end up with, we want delta of 0 or delta of t 0. Right? And if we work through the same thing, we end up with time equals 0.18 hours. All right, so
wait, did the original problem ask for the immediate elongation time or the immediate amount of elongation?
oh, yeah, that's
So
for
we've
the
just chosen an amount of elongation.
yeah. So yeah, you're right.
Should we look at the elongation at 5% of the relaxation time, or like 5% of the 27 hours we just?
Oh, I skipped a part. I asked for the relaxation time earlier, right?
That's the 27 hours that we just got.
Well, that's the infinite time. The relaxation time is a convention. So in the reading, the relaxation time is just defined as 90% drop of stress, right? So that works out to be about 10 hours. I'm sorry. Right? I asked about the relaxation time earlier and then never calculated it. Right. It's the time for the relaxation modulus to drop by a certain fraction. Again, it's just a convention. Right. But so this is what I wanted to show here was just the short time behavior versus long time behavior. Right. So short time behavior is 0.2 hours. What's that in minutes? Right. Yeah. It's, right.
12 minutes.
So yeah, something like that. So roughly 10 minutes, right, is what you can consider short time. And then long time is roughly a day. And anything in between it, then you have things are changing. Yeah.
So for this type of question, like asking about the immediate elongation, you need to know either the amount of elongation or the time, or you need to define it.
Yeah, so the immediate elongation is you evaluate that sum at 0, right? Your stretch equation at 0, which is just 0.2.
But I mean, here you
I mean,
define,
0.05, I'm sorry.
you define 5% as the immediate elongation amount. Is that convention, or like
It's just a convention, right? You have to pick something,
okay.
right? And so I picked 95%. We picked 95% for both, right? And that's just because that's basically the same kind of convention that the reading that I gave uses in some of the problems. So then the last real fast thing is if we load it up, if we load it for 5 hours and then remove the load, right? I want to plot the elongation, plot delta as a function of time for over a day. So I'm going to load it, unload it, right? So I'm going to have a curve, right? I load it, I'm going to have something that I get my curvature is the right way. Right? Is going to decay something like this. Right? So how do I find it? Well, we already know what the elongation before is, right? Right. That's just for 2/3 times our original curve. Right. So the strain at time, right? The strain at time t greater than 5, right, is, we can use just our Boltzmann superposition, right? So we can add 400 newtons to it at the beginning, and then at time t we can consider adding a load of negative 400 newtons, right? So our strain, sigma naught, right, where u naught is 0 and u1 equals 5 hours. Right? We just add our terms together, right? So we know what our elongation is for time 0 to 5. So 0 less than t less than 5, right? Right? And then for t greater than 5, right, we have exp. I'm gonna write this on a separate line so I can write it neatly. Right? We're just adding a negative load with a time shift of 5, right, of when we add it on. Right? So this is our Boltzmann superposition, right? We can think of, when we think about creep, right, we go back basically to the beginning of history, right, to what everything that we do to this.
Would you mind going back to the previous slide? Can you?
I don't know if I can. Which slide was it?
I just didn't have time to write down the last equation you wrote.
Oh, the strain equation?
I think so.
Yeah, so I'll just write it here again. Right. So u naught is 0 hours. Right. And u1 for our case is 5 hours. 5 showers. Right. Sigma naught is 400 newtons, and sigma 1 is 0 newtons. right? Right, and then I can just keep on adding terms, right? If I do more and more operations to this, right? And eventually, at long times, these both go to the same equation, right? We end up with 0.2 minus 0.2, right, is 0. Right? So that's it for today. On Monday, we will look at some of the homework problems that are due next week. And I'll take questions on the homework problems. Right. Yeah, so turn the homework in, just stick it up here.